Yeah, in the last class we have discussed Joule-Thomson coefficient at normal temperatures and low and moderate pressures. Now in this class we shall see how the Joule-Thomson coefficient value changes when the pressure is high and the variation of temperature. So now we are going to work on again Joule-Thomson coefficient, and we know its expression as dou T over dou P. Constant enthalpy is negative 1 over Cp dou E over dou V at constant temperature times dou V over dou T, sorry, dou E over dou P at constant temperature plus dou PV over dou P at constant temperature. So in the last case we have proved that this is a negative term, always negative term, and when the temperature is not normal temperature, ambient temperatures, and the pressure is not very high like low and moderate pressures, then this term is a negative term. But this term is going to be a positive term. So this is a negative term and this is positive term. Negative and positive. So what happens basically, this value is going to be smaller value, and that makes mu jt, this is Joule-Thomson coefficient value, becomes smaller and smaller and finally reaches 0 at some point. And that point is known as a inversion temperature. So let's see how it works out. Now when the pressure is high, at high pressures, if we have seen the graph of PV versus P, most gases have the PV value greater than the ideal gas. So therefore, the PV actually has a positive slope there. So therefore, dou PV over dou P at constant pressure is positive, and this value is keep on increases with increase in pressure. So what is happening? This term value is keep on increasing. It's a positive number, but with the increase in pressure, it becomes bigger and bigger. And at one point of time, this value and this value becomes equal, and this is a positive value and this is a negative value, and therefore this becomes 0 overall at a particular temperature. Now, and what happens after that, this value keep on increases. So with the increase in pressure, the Joule-Thomson coefficient value keeps on decreasing and finally becomes 0 when these two factors are equal. So further increase in the pressure makes this term more positive, and this is smaller number in the magnitude compared to this number. Therefore this total two factors inside this bracket becomes a positive number. Therefore mu jt becomes negative number. So therefore when pressure is too high, so mu jt becomes negative. So mu jt means dou t over dou p at constant enthalpy is becoming negative. What does it mean? So it is expansion. Therefore delta P is negative. When the gas expands, the final pressure is less, initial pressure is high. Therefore final pressure minus initial pressure is basically smaller number minus bigger number, that is a negative number. And we should have a negative number as a overall answer in this expression. So the change in pressure is negative. To get negative, the numerator delta T must be positive. So that means what is happening? The pressure is dropping when pressure is dropping. That means expansion. When expansion happens, the temperature of the gas increases. That means gas undergoes cooling effect. Undergoes, sorry, heating. Undergoes heating. And this is what happens above a particular temperature. So how the pressure increases? With the increase of temperature, pressure increases. Therefore, the pressure depends on the temperature. So therefore, it's a temperature where these two factors get equal, uh, and that temperature is known as the inversion temperature. And below that, the gases are expanded and they undergo cooling. But if they are expanded above that inversion temperature, they undergo heating effect. Now let's find out Joule-Thomson coefficient expression for real gases and inversion temperature. So what are we going to do now? We are going to find out expression for mu Jt and Ti. So we will find out this one. For which gases? For real gases. Now to get expressions of mu Jt and Ti for real gases, we should take the equation of real gas. And what is the famous real gas equation? That is van der Waals equations. Van der Waals real gas equation. And what is the van der Waals equation? Let's take for 1 mole of the gas, and that is P plus A over V square times V minus B is equal to RT. And this one, A over V square, we already know this is basically known as internal pressure. This is pressure correction. Internal pressure. And if we remember correctly, the dou E over dou V at constant temperature is called internal pressure, which is A over V square. Basically depends on the intermolecular attractions. Now let's try to do something here to arrive at the expression for mu Jt and Ti. So if we do the multiplication of these two linear expressions, linear polynomials, what we get here? Pv minus Pb, Av square times V is A over V minus AB over V squared is equal to R. And we know that for many gases A and B values are very smaller. Therefore, AB over V square is almost negligible. This is almost negligible. So what we end up? We end up with the equation that is PV is PV is, now I bring this, yeah, I bring okay, let's write this one. So PV minus PB plus A by V equal to RT. So we can rewrite this equation. PV is equal to, how do we write this? RT minus positive A over V. When it comes to right side, it becomes negative A over V plus PB. So I write that one as BP. Okay. Now what we do here? So let's try to divide this equation with P on both sides. Therefore, we get an expression that is V equal to RT over P minus, let's go back. So A over PV, A over PV plus BP over P, that makes B. So BP over P, that makes it simply B. So here we have a uh, the volume expression, and again here we have again value. So therefore we try to have only pressure and temperature terms on the right side, volume term on the left side. So therefore we make small approximation here. So we know that PV equal to RT for an ideal gas. So this is approximation for purpose. So therefore I can replace this PV with RT. Therefore we get RT over P minus A over RT plus P. And if we remember correctly for the mu jt expression, what we have, negative 1 over Cp do E over do V at constant temperature times do V over do P plus do PV over do. This is what we have. Okay, so to get that one, let's try to have this is what we need to find out. So let's take, now I have this expression. Now what I do, I try to do differentiation with respect to t on both sides. Okay, so what are we doing here? So differentiate on both sides with respect to temperature. So therefore at constant pressure, so keeping the pressure constant, so therefore dou V over dou T at constant pressure is going to be, so R is a constant and we are doing the differentiation keeping the pressure constant. Therefore the differentiation of T with respect to is 1. Therefore this one simply becomes R over P minus A over R, and we have 1 over T, and 1 over T difference is negative 1 over T squared. So therefore negative of negative 1 over T squared, that makes positive. So positive A over RT squared plus, what is the differentiation of B with respect to temperature? B is a constant, therefore it is simply 0. So this is what we have, the expression for dou V over dou T at constant pressure. Okay, so now what we do, we have PV equal to, yeah, so let's try to simplify this equation. So we come with the expression other way. We have RT equal to PV plus AP over RT minus BP. Okay, so now from this from where I got this equation, now you can see that equation, this one here. Oh, let's go back, this one here. So RT is equal to PV plus A over V plus BP. So I replace the V with RT over P. That makes this equation. So we get this equation. Okay. So what I do, RT is equal to, now we have PV and BP. So that means I can take the common factor P here, and this is V minus B plus AP over RT. So now let's divide on both sides. Let's divide both sides with PV. So what we get here, not PV, with PT. So RT over PT, that is we get R over P is equal to, so P dividing this will cancel out P here, and we get V minus B over T plus AP over RT times PT, and P cancel out, we get A over RT squared. Okay, now when we are doing the dou V over dou T at constant pressure, we got an expression R over P plus A over RT squared. Okay, now let's go and substitute this R over P, this one. So okay, this one we substitute in the place of R over P here. So dou V over dou T at constant pressure is V minus B over R, V minus B over T plus A over RT square plus A over RT square. I'm sorry, here we have T square. I'm very sorry, I did not write the T square. So therefore I get dou V over dou T at constant pressure is equal to V minus B over T plus A over RT squared plus A over RT squared. And what is the expression we are going to get? So V by T minus B by T plus 2A over RT squared. So I get dou V over dou T at constant pressure is equal to V over T minus B over T plus 2A over RT squared. So why I'm doing this dou V over dou T at constant pressure? There is some purpose for this. Okay, now let's do multiplication with T on both sides. Multiply both sides with T. So what does it give us? It gives us T times dou V over dou T at constant pressure. So multiplying this one, and we can distribute temperature to all these three terms. This gives you V minus B plus 2A over RT. This is what we get. Now if I do some kind of rearrangement here, T times dou V over dou T at constant pressure minus V is equal to, I have 2A over RT minus B. This is the expression. We have T times dou V over dou T at constant pressure minus V. So there is a thermodynamics equation. So we have another thermodynamic equation, that is volume is equal to T times dou V over dou T at constant pressure plus dou H over dou P at constant temperature. So from this what we can write? So dou H over dou P at constant temperature is equal to T times dou V over dou T at constant pressure minus V. And this is what we have got in the last time, that is T times dou V over dou T at constant pressure minus V equal to 2A over RT minus B. So what I'm writing here, this one is 2A over RT minus B, this one. So this is T times dou V over, this one is 2A over RT minus B. So that's what we have here. So if I rearrange this one, so from this what I can write? So T times dou V over dou T at constant pressure minus V is equal to negative delta H over delta P at constant temperature. How? I brought the value to the right side and this one to the left side. So therefore positive value when it comes here, negative term, and this value when it comes to the other side becomes negative, and I wrote in opposite direction. So this one is basically, what is that? 2A over RT minus B, which is equal to negative dou H over dou P at constant temperature. Okay, this is a very special term, and this term is actually we have for Joule-Thomson coefficient. What is that? Joule-Thomson coefficient mu JT is equal to negative 1 over Cp dou H over dou P at constant temperature. So small changes. So I just bring the negative inside. So we get 1 over Cp negative dou H over dou P at constant temperature. Now I replace this with 2A over RT minus B that we have got earlier. So therefore I get mu JT, so is going to be 1 over Cp times 2A over RT minus B. So this is the expression for Joule-Thomson coefficient of a for a real gas. And what does it indicate? The Joule-Thomson coefficient depends on A, intermolecular fraction, and B, size of the gas particles. And here what it indicates, there are three situations we get. If 2A over RT is greater than B, so that gives mu JT is a positive term. So that means that's a cooling effect. So when pressure drops, temperature drops. And when 2A over RT is less than B, then mu JT is positive. That means which effect is that? Heating effect. But another condition, when 2A over RT is equal to B, the mu JT is going to be 0. That means there is no heating and cooling effect. It's an ideal character. So therefore that 2A over RT equal to B is possible only at a particular temperature. That temperature is known as a inversion temperature. Inversion temperature. So therefore I can replace this T with temperature at the specific point as Ti. That is RTI is equal to B. So from this what I can get? Inversion temperature Ti equal to 2A over RP. This is the expression for inversion temperature of a real gas, which only depends on A and B of the gas. And it's very, very important. So A and B values decides the inversion temperature of a gas. If A and B are very small, if A is very small basically, then what it is going to be? When A is very small, inversion temperature is very small. In the case of helium, where the A is very little, therefore inversion temperature is very small. Therefore, to make these gases, helium like hydrogens, where they have intermolecular forces constant A is smaller, that makes their inversion temperatures much smaller value. Therefore, these gases undergo Joule-Thomson cooling effect only at much lower temperatures. And this Joule-Thomson effect can be used to liquefy the gases. In fact, so Linde's process and Clark's process use Joule-Thomson effect to make the gases into liquids. So this is the Joule-Thomson effect and inversion temperature for real gases. In the next class, we are completely entering into the new domain, that is thermochemistry, where we handle heats of reactions, heats of neutralization, heats of formation, standard conditions, heats of combustion, heats of reactions from enthalpies of products and reactants, and also Hess law of heat summation, and one more thing, the dependence of enthalpy of a reaction and temperature, which is basically Kirchhoff equation. So all those things will be covered in the next classes. And one more thing we are going to cover, the measurement of heats of reactions, that is calorimetry. How do we measure the heats of the reactions? And those things also will be covered in the next sessions. Thank you very much.